Hey everyone, in this video I'm going to be talking about electromagnetic radiation and the electromagnetic radiation spectrum. So first of all, electromagnetic radiation basically is caused by some sort of disturbance. Kind of like if you put a rock in a pond that was perfectly still, you would see the ripples from you dropping that rock. You've disturbed the water and now you see energy kind of moving out from where you disturb the water surface. It's kind of a similar idea, except for this time we're disturbing atomic particles. Okay, usually electrons, maybe they're being moved or accelerated by some sort of field, like an electric field. Okay, what happens is it produces an electric and a magnetic field that travels away from that disturbance. These different fields are moving kind of at right angles to each other, and they're moving at the speed of light. So if we're looking at this picture, we would have one of the fields kind of going up and down, the other field kind of moving in and out of the page, which is kind of hard to see because everything is 2D. So electromagnetic radiation is these different types of fields, the electric and the magnetic field moving in a different kind of frequency or wavelength. So just like the sound waves that we hear different pitches of sound based on the type of wave that it is. It's kind of like that, but we have different types of waves produced for each type of radiation. So the frequencies and the wavelengths are going to be important when we look at that. Our eyes only have the ability to see one of the types of radiation, okay, which is called visible light. We just don't have sensors in our eyes to absorb any of the other types of radiation, so we can't see any of the other types. They're invisible to us. So the types of electromagnetic radiation are like radio waves, or microwaves, or infrared. Okay, visible light, the ones that we see, is right in the middle. Ultraviolet, X-rays, and gamma rays. So when you go and look at this spectrum, they always get put in this order from radio waves to gamma rays. The actual individual type of radiation also has a little bit of a spectrum kind of included in it. So for example, visible light, when we look at white light, it actually is made up of all of the different colors of the rainbow, which means that each type of color has a different wavelength, okay, within kind of this area. Radio waves, so this side of the spectrum, have really low amounts of energy, which means that they're not going to affect your body tissues as much. They have a really low frequency, so the waves actually don't come along as frequent because they're so long. Okay, they can travel sometimes, like the wavelength could be like 1,000 kilometers. On the other side of the spectrum, and as we move up, we get higher and higher amounts of energy. The frequency increases because the wavelengths are so much smaller. So gamma radiation is really, really, really tiny and can actually fit through body tissues because the waves are so closely packed together. So the difference between frequency and wavelength, we measure frequency as the number of times we see a wave per second, which is in hertz, and wavelength is the actual measurement between each wave. So the length of the wave in meters. So if you notice that if you have a longer wavelength, your frequency would be low because that just means we're not seeing the waves as frequently. If your wavelength is shorter, if they're closer together, that means that your frequency is going to be higher because you're seeing them more frequently. So breaking it down between all of the different types of things that we see on the EMR spectrum, radio waves is the first. So remember, it has a really low frequency, about 3 hertz. Its wavelength is really long. It could be about 100 kilometers, okay, or sometimes even more, sometimes a little bit less. These are kind of just approximations. And there's a bunch of different things that cause radio waves. So in nature, we can see radio waves coming from lightning, sometimes astronomical objects, okay, but we create radio waves in transmitters and we can receive them in receivers, okay, using things like antennas. And it has a very, very, very small amount of energy. So 4 times 10 to the negative 19, and I put it, this is what the normal number would look like, not in scientific notation. Some of the things that we can use radio waves for are like TV and radio, okay, satellite signals, air traffic control, telephones, all of those things use radio waves. So I would say a lot of really important things that we use on a day-to-day basis. Microwaves are the next one on our spectrum. So they're going to be a little bit more frequent because their wavelength is a little bit shorter. So they're about 1 meter. Okay, again, it's an approximation. So they come from an electron tube inside the microwave oven that you guys probably have in your house. What they're doing is kind of disturbing these electrons in the tube, going back and forth and back and forth. And what it does is creates heat inside the water molecules in the food, and that's what cooks the food. So if you had something in your microwave that was really dry, it might not actually heat up that well because it doesn't have enough water in it. Just a fun fact. The energy for microwaves is a little bit higher than it was in radio waves, but still not super, super high. And some of the things that we can use it for, obviously, microwave ovens. Okay, things like wireless networks, radar, satellite and spacecraft communication, cancer treatments, remote sensing, and radio astronomy. So those are all things that we can use the microwaves for. Infrared is the next one on our list. So again, it's going to be a little bit more frequent because the wavelength this time is a little bit smaller. So this time about only 1 millimeter. Radiation from infrared comes from thermal. So anything that has some sort of temperature would radiate infrared off of it. Okay, that's why if you use an infrared camera, you can see the different colors. This energy is a little bit higher, but still not super, super high. You use it for night vision goggles or meteorology or thermal imaging cameras. Okay, you can use it to track like animals and stuff like that. We use it in fiber optic cables, and also if you're turning on your TV with your remote, okay, usually use infrared as well. Visible light, so remember this is the one that we can actually see with our eye. It's because we have these things in the back of our eye called rods and cones, and they are able to absorb the wavelengths of the rainbow. So frequency, this is like smack dab in the middle of our spectrum. So again, a little bit more frequent than the infrared, and the wavelength is going to be a little bit smaller. So this time 740 nanometers. The source, okay, lots of things create light like the sun or different types of light bulbs. Okay, fire, anything like any sort of reaction that gives off light we can see. And remember that visible light, usually if we're looking at white light, it is actually made up of all of the different colors, and each color has a specific wavelength. So I said about 740 nanometers, every color would actually have its own separate wavelength that we could write down. Energy, again, is going to be kind of smack dab in the middle, not super high, 1.8. Is kind of right in the middle. Ultraviolet light. So now we're moving into the other side of visible light. So we're going to get even more frequent, and the wavelength is going to get even smaller. So ultraviolet light is where it starts to become what we call ionizing radiation. So this is where we can actually start to potentially harm our body cells with it. So we know that being out in the sun or going into tanning beds can increase the chance of you getting skin cancer. Okay, it's because ultraviolet has a little bit higher energy, and the wavelength is a little bit smaller, so it actually can get between your cells and kind of potentially mess up the DNA. But we use ultraviolet light sometimes in like medical or dental practices, like they're killing bacteria. Sometimes they use it to cure ink. Sometimes they use it in something called phototherapy, or if you're sun tanning outside, that is the radiation that you're absorbing into your skin in order to get tanned, which also helps you make vitamin D. X-rays. So everyone in here should have had an X-ray at least on your teeth before, but maybe if you broke a bone, you got an X-ray to see it. This is where we are starting to get really, really frequent. Okay, the wavelengths are tiny, 0.01 nanometers. So this again is coming from an electron moving from a higher energy level to a lower one. So imagine in the actual atom, we have electrons that occupy certain levels, and the electrons are moving from maybe the outer level to the lower one and going back and forth, and that's allowing energy to be released. So this is kind of simulated in an X-ray machine, but X-ray radiation can come from different elements like radon, okay, and other radioactive elements that we have on the periodic table. its energy is a little bit even higher. That's why we don't want to get X-rays all the time, and why you have to wear a lead vest over top of you if you are getting X-ray on your teeth, because radioactive material from X-rays can be a little bit more damaging to our cells. We use them for X-rays to check broken bones or pneumonia. Okay, also things like mammograms to check for breast cancer would be using X-ray technology. The next type, the last type on our list, which would be the most damaging to our cell because it's the most frequent. It has the tiniest little wavelength, so about 1/1,000,000,000th of a meter. Okay, really, really, really tiny. They come from nuclear explosions or lightning, or if an actual element is breaking down, okay, or decaying, it will release gamma rays. So this energy is incredibly high. That's why gamma rays are so damaging to our cells. So nuclear power plants can give off gamma rays. They also use it in different things called radiotherapy, or sometimes industries will actually use gamma rays to sterilize or disinfect tools or things that they're using. So when we're talking about the energy, the wavelengths, the frequency, we have to kind of refer back to the effects on the body. So the two different types of radiation that you have are non-ionizing or ionizing. So the first couple, radio waves, not super damaging. Okay, microwaves, not super damaging. Again, we don't experience super high levels of these waves, so it's not going to affect our bodies excessively. Obviously, if you experience high amounts of microwaves, it can cause burns. Okay, most radiation could cause burns if you get a lot of exposure to it. All of these are non-ionizing radiation, but there are things that can happen if you expose your body to a lot. So for example, infrared, there's like filters that you can have on your glasses if you were someone that was looking at infrared a lot. Okay, visible light, again, we look at it all the time. But if you're like super exposing yourself, obviously it could damage the skin. And then we move into the ionizing radiation. So ionizing radiation can actually go into the DNA, and it can actually break the bonds in the DNA, which would obviously cause the DNA to break open. Sometimes our body can replace those mistakes or fix the mistakes as they happen, but if they're happening at a really high rate, your body might miss those mistakes, and then that cell might end up not basically functioning properly or dying at the end. So UV, X-ray, and gamma radiation are all examples of ionizing radiation. As you go down the list, they're going to become more and more damaging to our cells. So gamma rays, because the energy is so much higher than UV, you would not want to expose your body to a lot of gamma rays. UV rays, we obviously expose our body to all the time, every single day that you're out in the sun. So we are supposed to be wearing sunscreen when we're doing that to kind of protect from some of these UV rays that could potentially cause cancer. But gamma rays would be like way quicker if you were doing or exposing your body to a lot of it. So basically that's all I want to talk about for now about the electromagnetic radiation spectrum. I will be explaining a little bit more in another video.